Welcome. My name is Randy Ellis. In this session, we'll go over some of the prerequisite material related to a vector space. The main concepts for this session are: what is a vector space? We'll briefly state the axioms of a vector space, but we won't explore them in detail. What we'll do instead is we'll look at some of the properties that a vector space has. Let's look at a simple example. Suppose we're given three vectors. A1 has entries 1, 2, 1, A2 has entries 2, 4, 2, A3 has entries 1, 0, 1. And we ask, what space do these vectors live in? Well, a superficial answer would be, because there are three entries, they live in the space R3, and they certainly do. But let's look at these a little more closely. We see that we could derive A2 as a scalar multiple of A1, specifically that 2 times A1 equals A2. Another way to say that is that 2 times A1 minus A2 equals 0, and that means that A1 and A2 are linearly dependent. Now if we look at A2 and A3, we see that no non-zero multiple of A2 produces A3. So A2 and A3 are linearly independent. So this idea suggests that there are only 2 degrees of freedom in this set of vectors, but we really don't know what that means or how we can talk about that in a more rigorous way. The concept of a vector space is this: a space is a set with some specific added structure. A vector space, particularly, is a set of vectors that satisfy some simple properties. Recall that for us, a vector is a finite list of real numbers, and we're going to write the space that a vector lives in using these scripts. So we'll use the script v, the script w, sometimes the script u, and so on as needed. And these spaces can be defined constructively, saying here are some examples and rules to get them, or by restriction, saying here are some size m vectors that cannot be in the space. And the constructive method is to give some specific instances of v, and then a restriction, we have some larger space, and then we have some rules that narrow it down to vectors in the space v. So here's the abstract definition. A vector space has to have a field. Now, for us, that means the real numbers, and yes, you could define them over complex numbers and rationals, but we're only looking at vectors that have real entries. So each vector in the space must have the same number of entries for us, and there are 2 operators that are for closure. If alpha is in your field, which for us means alpha is a real number, and u is in your vector space v, then alpha times u is in your vector space v. And similarly, if you have a pair of vectors, u and v, in the space, then their sum is in the space. And these are quite similar to the basic operations that we had for vectors. And now what we're starting to do is we're starting to describe some of the properties of a vector space. So as I commented earlier, for us the field is always the real numbers, and the vector space are always finite vectors represented as columns. These are the axioms of a vector space. You can find these in many textbooks on linear algebra. I hope that you've gone through these in your prerequisite courses. We won't go through them in any detail. We're more interested in how to use them, that is, in their computation. So for us, a vector is an ordered column of real numbers, must be finite. All vectors in the space we're looking at must have the same size, which means that we can represent any vector u in the space using a set of m real numbers that are put into a column. Multiplication and addition are interpreted as the usual way. If we have some value beta and we multiply it by u, that's equivalent to saying that the first entry of the product is beta times u1, the second entry is beta times u2, and so on until the nth entry. And then vector sum is defined the same way. So the same way that we did when we were looking in vectors. So here's our interpretation of a vector space. We interpret these axioms very simply. If u is a vector in the vector space, and v is a vector in the vector space, and alpha is any real number, and beta is any real number, then the linear combination alpha times the vector u plus beta times the vector v has to be in the same vector space. This relates to all of the axioms that are stated regarding distribution, commutation, and so on. All of these come from our interpretation as an ordered column of real numbers. And it's important, 0 is always in the vector space. We can see that by setting alpha to 0 and beta to 0, and this property requires that 0 also be in the vector space. For examples and counterexamples, I'll refer you to Dr. Gilbert Strang's excellent series of textbooks. So the simplest example, the one that you're probably most familiar with already, is called the coordinate space. It's also called the Euclidean space or real space. It goes by many names. Coordinate space is currently the most common formal term for it. And we write this as real numbers to the power m, and these are vectors of having m entries. So our previous example was the plane, which is the Euclidean space, and here any vector in it has 2 entries that may be the same, they may be distinct. Our previous example was specific vectors in R2. Here, if we have a vector u where the first entry is a real number and the second entry is 0, this satisfies all of the axioms of a vector space, and in particular, if we have u and v that are like this and we take a linear combination, the linear combination will result in a first entry of u plus v and a second entry of 0. So one way that we can think of a vector subspace is it's a linear subset of a vector space. This idea of a subspace is really powerful and something that we'll use often in our course. So what we say is that it's a subset of a larger space. Now this subset or equal means it doesn't have to be a proper subset. That is, it's possible that W equals V, although the ones that we're interested in are where W is a proper subset of V. This has to be linear and closed. So for any U in the subspace and V in the subspace, the same linear combination rule has to apply. So W is itself a vector space. So we can have a little vector space W inside a bigger vector space V, and that is okay. So some geometrical interpretations are, suppose we're looking at coordinate space of size 3, which is just our 3D space. A one-dimensional vector subspace is a line that goes through the origin, and a two-dimensional subspace is a plane that goes through the origin. Note that it has to contain the origin. So dimension. For us, the dimension refers to a vector space. It doesn't refer to the number of entries each vector has. So a dimension is the minimal number of vectors you need to construct your vector space. So for example, if your vector space is coordinate space 2, 2D, plane, however you wish to refer to it, and you say that all vectors must be of the form, they must have a real number in the first entry and 2 times that real number in the second entry, then what that gives us is a vector space. So the vector u is of size 2, but the space it specifies is only one-dimensional. And geometrically, this happens to be a line through the plane, and it has a slope of 2. So a restriction form for the same space would be, say, all vectors that are orthogonal to this particular vector are 0. And I'll let you work it out that this definition and this definition provide the same vector subspace. Now let's look at the geometry of a vector space. Suppose that we have our coordinate space of size 2, r squared, r2, the plane, however you want to refer to it, and here I've drawn coordinate axes that are pictorial only. This green line is a vector space, and this red line is not a vector space. The difference is that the green line goes through the origin, or the 0 vector, and the red line does not. A vector space must contain the 0 vector. So in summary, what do we have? A vector for us is a finite column of real numbers. A vector space is a set of vectors that has structure. We can see now that this is an infinite set, although the dimension for us is always finite. A vector space has closure under scaling and addition. Euclidean space is one example, referred to technically as the coordinate space. A subspace is a vector space that's inside a larger set, and a vector subspace must always contain the zero vector.